Okay, so let's begin with the next chapter, electric potential and capacitance. So we have studied potential earlier in the context of gravitational potential, right? Same thing we'll do for the electrostatic force also. So first of all, we'll find out the electric potential due to a point charge. Okay, and for that, we are going to find out the work done against the electrostatic force. Okay, so let's suppose we have this charge, let's call it capital Q, and suppose there is some other charge, small q, it is at very large distance away, suppose it is at infinity, and you bring that charge from infinity and you keep it at some distance, let's call it distance r, away from point charge capital Q. Okay, so you are bringing this charge, the part doesn't matter, okay, like this, and you keep it ultimately at this much distance. Okay, so this distance is small r away from capital Q. So now what will happen in doing this? So when you move that charge, there will be a force acting on this charge due to this charge, right? So when you move it closer to the capital Q, it will oppose it. Okay, if both charges are positive, then it will oppose it, right? So you have to do some work against this opposition. You have to do some work against this force, the electrostatic force between the two charges, in order to move it closer to the capital Q. Okay, so let's find out that work. So let's suppose that we are bringing the charge small q from infinity. So we bring small q from infinity and we keep it at distance r. So we bring it from infinity to distance r away from capital Q, right? So it was at very large distance. Suppose we have brought it till this point. Okay, this is finite distance, right? So we have brought it till this much distance. So this is some intermediate point. Let's call this much distance x. So x is some intermediate distance along the way. Okay. So now see, now it is at distance x away and you move it little bit closer. So let's suppose you move it by this much distance. Let's call it dx. So there will be some work done against the electric field due to this charge capital Q, or force due to this charge capital Q. Okay. So what will be that work? So work done to move charge small q by distance dx, by distance dx, closer we can say. So that work done is suppose dw, and we are doing that work against the force due to capital Q. So I will say work done against capital Q, against capital Q. So that work done will be equal to what? Minus of force due to capital Q on small q multiplied by this distance. So work done is force multiplied by displacement. Okay, but why am I taking this minus sign? It's because of we are doing work against the electrostatic force. Okay, so what is F? Where F is the electrostatic force between two charges, that is 1 upon 4 pi epsilon naught multiplied by q times q divided by x square, because they are at distance x away from each other. Okay, so now let's substitute that. So see, Now suppose it is initially at infinity. Okay, so suppose it is initially at some point A and we move it from point A to the point B. So suppose we move the charge small q is moved from point A to point B. Then work done in doing so. How much would be work done against the electric field due to capital Q? I will just say capital Q. It means that electric field due to capital Q. So work done against capital Q in doing so. Okay, in doing so, it will be the integral of this dw, right? It will be integral of dw from point A to B. So we can say W is the work done when we move it from A to B. So it is WAB suppose. So WAB is the work done to move it from A to B. So it is integral of minus of f dot dx from the initial distances Ra and final distances R suffix B. Okay. So this is equal to. Now we can take minus sign outside. So it is integral from Ra to Rb of f dot dx. And what is f? F is this much. Okay. It's 1 upon 4 pi epsilon naught q times q divided by x square dx. And then what we can do is we can take this 1 upon 4 pi epsilon naught q times q outside. So we get minus of q times q divided by 4 pi epsilon naught multiplied by its integral of 1 upon x square dx, or I can write it is x raised to minus 2 dx. Okay, integral of this thing from Ra to Rb. Okay, so what will be its integral? Its integral is x raised to minus 2 plus 1 divided by minus 2 plus 1. Okay, we know integral of x raised to n dx. Integral of x raised to n dx is x raised to n plus 1 divided by n plus 1 with proper limits, right? So we have n equals to minus 2. N is minus 2. So it is x raised to minus 2 plus 1 divided by minus 2 plus 1. So what do we get? We get WAB. Therefore WAB is equal to q times q minus q times q divided by 4 pi epsilon naught x raised to minus 2 plus 1 is minus 1 divided by minus 1. Okay, and it is from Ra to Rb. So we can take this minus 1 outside. So that minus 1 multiplied by this minus 1 gives us plus 1. So it is equal to q times q divided by 4 pi epsilon naught, and x raised to minus 1 can be written as what? 1 upon x from Ra to Rb. So lower limit is Ra, upper limit is Rb, and that is equal to, we can say, q times q divided by 4 pi epsilon naught 1 upon Rb minus 1 upon Ra. So this is the work done to move the charge from point A to point B. Okay, is it clear? All right. So this work done gets stored as the potential energy of this system of charges. This work done gets stored as the potential energy of the system of charges. Okay, so this is equal to change in potential energy. So we are moving the charge from point B to A. So this work done gets stored as potential energy of system of charges. System of charges. Okay. So potential energy at point A. Okay. So Preeti, is it clear to you or shall I explain once again? All right. So work done. So see, we are moving this small charge, small q from infinity and we'll keep it at distance r. Okay. So now suppose we take some initial point A, final point B. Okay. Abstract points. Okay. Then finally we will call them infinity and r. Okay. So let's suppose the charge small q is at point A. We move it to point B. So we have to do some work against the electric field of charge capital Q. And because we are doing work against the electric field, that means we have to supply energy from outside, right? So this work done gets stored as the potential energy of the system, okay, system of charges. We have calculated this formula for the work done. So this is equal to final potential energy minus initial potential energy. This work done is change in potential energy, okay. So we can say that change in potential energy is final potential energy at point B minus potential energy at point A. A is our initial point. So it is equal to what? It is equal to Q multiplied by Q divided by 4 pi epsilon naught 1 upon RB minus 1 upon RA. Okay, so A is initial point, B is final point. So now this is general expression for change in potential energy, right? So see, what we can measure is we can measure only change in potential energy and not the individual potential energies at point A and at point B. Okay, we can only measure the change in potential energy and not the exact potential energy at point A or at point B, right? So for that, now what we are going to do is we are going to use a convention. So it's similar to what we did in case of gravitational potential. So suppose that our initial point is infinity. Okay, let A is at infinity and B is at distance r from charge capital Q. So therefore now our formula will become what? It is potential energy at the final point. Final point is at distance r minus potential energy at the initial point. So initial point is infinity. So it will be equal to work done to bring a charge from infinity to distance r, right? So it will be equal to, we can say q times q divided by 4 pi epsilon naught 1 upon rb. So final point is at distance r minus 1 upon ra. So it is 1 divided by infinity. It means that 1 divided by very large distance. So this thing will approach to 0. Okay, this thing is 0, right? So we get potential energy at distance r. That means when separation between two charges is r, potential energy then minus potential energy at infinity is equal to what? Work done to bring charge from infinity to r. And that is equal to, because this thing becomes 0, we can write this as q divided by q upon 4 pi epsilon naught multiplied by 1 by r, or we can write it as 1 upon 4 pi epsilon naught multiplied by q times q upon r. Okay, so then see, we can measure only difference in potential energy. So here we make use of a convention that potential energy at infinity is equal to 0. Okay, so this is just a convention, right? Because we can just measure the change in potential energy and not the exact potential energy. So we set this equal to 0 so that we get a simplified formula for potential energy. Okay, so we assume that u at infinity is equal to 0. Potential energy when the distance between two charges is infinity is 0, and therefore we get potential energy at distance r equals to 1 upon 4 pi epsilon naught multiplied by q times q divided by r. Okay, we get potential energy equals to 1 upon 4 pi epsilon naught multiplied by q times q divided by r. Right? So is it clear? Yes, no? So then, okay, this is potential energy when distance between two charges is smaller. Okay. Now, next we are going to define the electric potential, or you can say electrostatic potential due to a point charge. Okay. So let's define the electrostatic potential due to a point charge. What is this? So it is defined as work done to bring a unit positive charge from infinity to distance r away from this point charge. Okay. So we can say, let's suppose I want to find out, let's suppose I have charge capital Q and I want to find out potential due to this capital Q at distance r away from this capital Q. Okay, so I will say potential due to Q at distance r away from this charge capital Q, it is equal to work done to bring small q from infinity to r. Okay, work done to bring it from infinity to r divided by the charge small q. Okay, so potential due to capital Q is denoted as V due to capital Q. Okay, it is denoted as V, and because of this charge capital Q, we have put the suffix capital Q. So it is equal to work done to bring a charge small q from infinity to r. We have calculated it. It is 1 upon 4 pi epsilon naught q times small q upon r, right? So it is 1 upon 4 pi epsilon naught q times small q divided by r and divided by this charge small q. So this q and q gets cancelled. So we get potential. Okay, I will just call it V at distance r. Okay, it is V due to capital Q. I have written it uh, in a form of a sentence, and I will denote it as V at distance r. Okay, so V at distance r is equal to what? This q and q gets cancelled out. So it is 1 upon 4 pi epsilon naught multiplied by capital Q divided by r. So this is potential due to one charge. Okay, work done to bring charge small q from infinity to r, and the small q is known as test charge. It is generally taken as positive, a small positive test charge divided by charge small q. Okay, next let us see potential due to n sorry point charges. Next let us see potential due to n point charges. So now we have n point charges. What will be potential due to them? So suppose this is charge q1 this is Q2, Q3, and we have n number of them like this. Let's suppose Qn, and I want to find out potential due to this system of charges at some point. Okay, so suppose this is the point, this is the point, right? So what will we do? It will be just addition of potential due to all charges. Okay, will it be scalar addition of or vector addition? Scalar addition, right? Why? Because how do we find the potential? How do we define the potential due to a charge? It is work done per unit charge. Okay, work done per unit charge to bring that charge from infinity to a point. So work is a scalar, work is a scalar, charge is a scalar quantity, right? So scalar divided by scalar will give us a scalar only. So potential is a scalar quantity. It's not a vector. Okay. So that means addition of potentials due to n number of charges is easy. It will be just a scalar addition. Okay. So this is suppose point P. Okay. So then suppose the of distance of point P from all the charges is distance from Q1 is R1, distance from Q2 is R2, distance from Q3 is R3, so on and so forth up to Rn. Then what can we say? So R1, R2 up to Rn are distance of point P from charges Q1, Q2, so on and so forth up to Qn. Therefore, potential at point P is just vector sum of potential due to all charges. Okay, potential at point P is equal to what? Potential due to first charge plus potential due to second charge plus so on and so forth up to potential due to nth charge. It is just scalar addition. So this is equal to, we can say 1 upon 4 pi epsilon naught multiplied by Q1 over R1 plus 1 upon 4 pi epsilon naught multiplied by Q2 over R2 plus 1 upon 4 pi epsilon naught multiplied by, okay, I can say plus so on and so forth up to plus 1 upon 4 pi epsilon naught up to Qn divided by Rn, right? So this will be the net potential, and we can write it in a form of a summation. We can take 1 upon 4 pi epsilon naught common. So it will be summation of, it will be, okay, let's write it. So if I want to write it in form of summation, so Vp will be just equal to summation of, we'll just make some more space. So Vp is just, you can take 1 upon 4 pi epsilon naught common, 1 upon 4 pi epsilon naught summation of Qi over Ri, and that I goes from 1 to n, right? So this will be total potential. This will be the total potential. Okay, so this is clear. So okay, so now we understand what is potential energy. Okay, what is electrostatic potential energy and what is electrostatic potential. So next we'll find out electrostatic potential energy of system of charges. Now here two cases will come. Okay, so the let's find out electrostatic potential energy, potential energy due to system of charges, system of n charges. Okay, let's find out the electrostatic potential energy due to system of n charges. And here two cases will come. First one is in absence of any external electric field, and second one in presence of some external electric field, right? So there can be an external electric field present in the space, okay, or it might be absent, okay. So suppose there are only n charges and you have to find out the potential energy. So see, okay, so let's assemble the system of n charges, okay. So let's consider case 1, that is in absence of an electric field, external electric field, okay. So now suppose there is nothing in this space. Right now there is nothing in this space, and you bring n charges one by one, okay. So now when you bring first charge, how much would be the work done? How much will be the work done when you bring your first charge? It will be zero, because nothing is opposing us. There is no electric field. There is no other charge which will oppose, right? So let's suppose charge, let's suppose charge Q1 is brought from infinity to some point, okay, to some position vector r1 bar. Let's call it r1 bar, right? So work done in this process, work done is equal to 0. So you have, let's draw some coordinate system. It's y and z, okay. This is my x coordinate, this is y coordinate, and this is z coordinate. So I'm bringing charge q1 and I have kept it here. Charge q1 is brought from infinity, no work is done. So now how much is the potential energy of this system? So potential energy is 0, right? So let's call this work done W1. So W1 is equal to 0, and therefore potential energy is right now equal to 0. So now this charge Q1 is kept at some position vector. Let's call that position vector R1 bar. Okay, with respect to some origin O. Now you bring second charge Q2 and you keep it somewhere, okay, in this space. So let's suppose we keep it at position vector R2 bar. So this is Q2 and we keep it at this position vector. Okay, this is R1 bar, this is R2 bar. Okay, so now Q2 is brought. So Q2 is brought, let's keep it assumed, okay, that it is brought from infinity to distance R2 bar, not distance, to position vector R2 bar. So now how much would be the work done in this process? Tell me. Now there is some charge. There is this charge Q1. Work done will be 1 upon 4 pi epsilon naught multiplied by Q1 Q2 divided by the distance between them. Okay, so this is your final point. Now distance will be this much, right? So distance is this much. Let's call it R12. This is, sorry, this distance is R12. Okay, so work done in this process. Work done in this process is, suppose W2. W2 is 1 upon 4 pi epsilon naught multiplied by Q1 Q2 divided by R12. And therefore now potential energy becomes, okay, W2, right? So now next you bring third charge. You bring third charge Q3 and you keep it at some location. So let's suppose we keep it here. Let's call it Q3. And this location is R3 bar. Okay, suppose this is R3 bar where we kept Q3. So now how much would be the work done? So now when you bring Q3 from infinity and keep it at R3 bar, you have to do work against Q1 also and Q2 also. Both are opposing it, right? So work against Q1 will be 1 upon 4 pi epsilon naught, that constant, multiplied by Q1 Q3 divided by this much distance. Okay, distance between them, final distance R13. And work done against Q2 will be 1 upon 4 pi epsilon naught multiplied by Q1 Q3 divided by this much distance, which is R23, right? So work done in this process. So now Q3 is brought, okay, from infinity to R3 bar. So work done in this process, W3 will be equal to what? Work done against 1 upon 4 pi epsilon naught. Work done against Q1. So Q1 Q3 divided by R13 plus work done against Q2. It is 1 upon 4 pi epsilon naught multiplied by Q2 Q3 divided by R23. Okay. So then if you bring next charge, you have to do work against all three of them. Okay. So on and so forth. Right. So how much will be the potential energy of these three charges only? So this process we can keep on repeating, right? We can bring n number of charges like this. Okay. But the concept is clear. Three charge, one charge, no work done. Second charge, there is some work done. Okay, against the first charge. You bring third charge, you have to do work against first and second. You bring fourth charge, you have to do work against first, second, third. Okay, so on and so forth. So how much would be potential energy? So potential energy of the system is what? Let's denote it by U. So U is equal to what? W1 plus W2 plus W3. So work done to bring charge Q1 plus work done to bring charge Q2 plus work done to bring charge Q3. It is 1 upon 4 pi epsilon naught. We can take out. Work done to bring first charge was 0. To bring second one is Q1 Q2 divided by R12 plus W3 is Q1 Q3 divided by R13 plus W3 is Q2 Q3 divided by R23. Okay, so this will be formula for potential energy of system of three charges. And for n charges, we can keep on doing this. Okay. So is it clear? Yes, no? All right. So this is in absence of an external electric field. Next case is in presence of external electric field. So next is case 2, in presence of some external electric field. Okay. Now we are doing the same thing. We are building system of charges and charges, but there is some electric field in the region. Okay. It might be uniform, it might be non-uniform. So I am drawing uniform electric field. Non-uniform can be anything, right? So suppose this electric field is present in this region. Let's call it E bar. And now you bring first charge from infinity and you keep it. You keep it somewhere. You keep it here, let's say. So when Q1 is kept, okay, Q1 is kept at location R1 bar. Will there be some work done? This R1 bar. Okay. So now, sorry. So now you have some electric field in this region and you take some charge, let's call it Q1, and you bring it from infinity and you keep it here, okay, at R1 bar with respect to this origin. So will there be some work done? Yes, no? Right, there will be some work done because this electric field is produced by some charges which may not be here in this part of the space. They are somewhere else, but their electric field is present here. Okay, this electric field is present here. So this electric field will oppose the motion of this charge, right? So when you are bringing this charge from infinity till this point, there will be some work done against this electric field. Okay, so how much is the work done? Okay, let's consider small displacement dr. So work done against the electric field for for small displacement small displacement dr bar. How much would be work done? So work done, let's call it dw. This is work done against the electric field, this electric field for small displacement of this charge. How much small displacement? Dr bar. So work done is equal to force times displacement, right? F dot dr, it is dot product of force to displacement, but we want work done against the electric field, so it is minus of F bar dot dr bar. Okay, and what is F bar? So this electric field will exert some force on this charge Q1, and that is F bar. Okay, so force due to E bar on Q1. Let's call it F1. So F1 bar, it is equal to the electric field multiplied by the charge. So it is E bar dot Q1 bar. Sorry, not Q1 bar. It is E bar multiplied by charge. Okay, charge is a scalar quantity, right? So F1 bar is E bar multiplied by Q1. So work done will be what? Minus of Q times E bar dot dr bar. Okay, so work done will be this much, and then work done to bring it from infinity to R1. So how much will be that? So work done to bring, sorry, this charge is Q1. Work done to bring charge Q1 from infinity to R1. So let's call it W1. So now when you bring first charge itself, there is some work done. So it will be integral of dW, and let's call this work done also dW1. This integral of dW1 from infinity to R1, right? And okay, we can write it down. So W1 will be equal to work done to bring charge Q1 from infinity to R1. And what is dW1? So it is minus of Q multiplied by, sorry, Q1 multiplied by E bar dot dr bar. So this much will be the potential energy. This much will be the potential energy of Q1 when you bring it from infinity to R1. Okay. So now it depends on the electric field. It depends on the electric field what kind of formula you get, what kind of final expression you get, right? So if E bar is directed along x-axis only, then movement along x-axis will only matter. Nothing else will matter. Okay, because this is dot product, right? So it depends on the nature of E bar, how much would be the work done. Okay, so now when you bring second charge, so when second charge in, when so work done to bring Q2, how much will be that now? So it will be, let's call it W2. So now you have to do two works. So first one is work against the electric field, work against the electric field, plus work against work against Q1. Okay, so work done to bring Q2 and from infinity to R, infinity to R2 bar. So how much will be that? How much will be the work done? So against electric field, now we just have to replace Q1 to Q2, this R1 to R2, because we are keeping it at R2 bar. Okay, so that much will be work done against the electric field. It is work done from infinity to R2 minus Q2 multiplied by E bar dot dr bar, right? Plus work done against Q1 is 1 over 4 pi epsilon naught multiplied by Q1 Q2 divided by R1. Okay, right? So this will be work done to bring Q2 from infinity to R2 bar. And let's bring one more charge. Okay, so work done to bring Q3 from infinity to R3 bar. So W3 is equal to this formula as it is, just R2 will change to R3. Okay, so it is work done against the electric field as work done against Q1 and work done against Q2. So here you can take 1 upon 4 pi epsilon naught common, right? Work done against Q1 will be Q1 Q3 divided by R13 plus work done against Q2 will be Q2 Q3 divided by R23. Okay, so now same thing will keep on repeating if you would keep on bringing a number of charges. Okay, there will be some work against the electric field, there will be some work done against the other charges. Okay, So the concept is clear now, right? So therefore the potential energy, therefore the potential energy of this system of charges, system of three charges. So what will be the potential energy? U is equal to W1 plus W2 plus W3. Okay. So which can be written as work done against the electric field. So now if you add them, you can take Q1, Q2 and sorry, you cannot take them common also. No, you cannot take, you can just take minus sign common, right? Okay. So it is minus of Q1 multiplied by work done to bring this charge from infinity to R1. Okay. E bar dot dr bar plus Q2 multiplied by same thing, work done to bring Q2 from again the electric field from infinity to R2 E bar dot dr bar plus same thing for Q3. So this is work done against the electric field, sorry, not minus, infinity R3 E bar dot dr bar. This is work done against electric field plus work done against the charges, which is 1 upon 4 pi epsilon naught. Okay, Q1 Q2 divided by R12 plus Q1 Q3 upon R13 plus Q2 Q3 divided by R23. So this will be the formula for three charges. Potential energy of three charges when external electric field is present. Clear? Yes, no? We'll see one more topic because see, actually we have seen some theory, but there are not many questions based upon this. Okay, so let's see one more topic. So let us see the electrostatic potential. Electrostatic potential due to an electric dipole. Due to an electric dipole. Okay, so we know what is an electric dipole. Electric dipole is a positive charge separated from same amount of negative charge by some distance, right? So let's suppose we have this electric dipole. This is our electric dipole, and this is charge minus q. This is charge plus q. Suppose this is point A, point B, right? And I want to find out the electric potential at some point, at this point. Okay, I want to find out electric potential due to this system at this point. Let's call it right here. At this point, let's call it P. Okay, so I have this electric dipole. Electric dipole is a positive charge separated from same amount of negative charge by some distance. Okay, then suppose minus q is at point A, plus q is at point B, and I want to find out the electric potential due to this dipole at this point, at point P, which is at some distance from the center of dipole. So center of dipole is suppose point O. Okay, so now let's join point P with the center of dipole. So it is at some distance, this much distance, let's call it R, from the center of the dipole, right? And this is electric dipole moment. We know electric dipole moment is directed from minus q to plus q. So the angle between this R or distance OP and electric dipole moment, or you can say axis of the dipole, is theta. This is the angle between the two, right? So let's find out potential due to this dipole at point P. So to find potential, let's join point P to positive and negative charges, right? So let's join it to positive and negative charges. So just at this much distance from positive charge and negative charge. Okay, so this point is A, this is point point B. So okay, what is sorry, what is R? Oh no, sorry. What is R? R is this distance. Okay, distance OP. So distance from negative charge is suppose R minus, distance from positive charge is suppose R plus. Okay, right? So what is R minus? It is distance of P from minus Q, and R plus is distance of P from plus Q. Then let's recall what is electric dipole moment. So electric dipole moment is a vector quantity. Electric dipole moment P bar is equal to Q multiplied by 2A bar. Okay, or you can write it as Q times 2A multiplied by P cap. So its magnitude is Q times 2A. What is 2A? 2A is distance between these two charges. Okay, so this distance is A, this distance is small a. So the total distance between two charges is 2 times A. So electric dipole moment has magnitude equals to magnitude of one of the charge multiplied by distance between two charges, right? So P bar is equal to this magnitude Q times 2A multiplied by P cap. P cap is directed from minus Q to plus Q. Okay. Now this is simple. So what is electric potential due to n charges? It is just sum of potentials due to all charges, right? So electric potential due to dipole, let's call it V, it's equal to V plus plus V minus. And what is V plus and V minus? V plus is potential due to positive charge, V minus is potential due to negative charge. Okay, so that is V equals to 1 upon 4 pi epsilon naught multiplied by plus Q upon R plus 1 upon 4 pi epsilon naught multiplied by minus Q divided by R minus. Okay, so this is just formula for electric potential due to a charge, and this is distance. Okay, R plus and R minus. Then we can take 1 upon 4 pi epsilon naught Q common from these two. So Q divided by 4 pi epsilon naught I will take common. So it is 1 upon R plus minus 1 upon R minus. Right. So now we have to find out this R plus and R minus. And we'll see a very simple method to find this out. Okay. So what we will do is we'll draw perpendicular from Q plus and Q minus on this line. Okay. So let me draw perpendicular. So if I draw perpendicular from plus Q, it meets at this point. Let's call this point M. Okay. And then I will extend this line. And I will draw perpendicular from minus Q. I will draw perpendicular from minus Q. So it meets at this point. So suppose this point is N. This point is N. So see, now R minus is equal to this distance R minus, which is distance AP. I can say it is nearly equal to this distance NP. Can I say this? Not exactly equal, it's nearly equal. Yes, no? Can I say this? Okay. So this approximation will get better and better if this distance is very small. Okay, so for an example, you take this point and this point. They are very close. Now you take this point, which is very far apart, and you join this point with this point and this point. Can I say this distance, which is, let's call it R minus or whatever, this distance and this distance, okay? Can I say they are almost equal? The point is very far apart compared to this distance. Yes, we can say this, right? Okay, this much distance and this much distance. So almost equal. So what we'll consider is point P is at very large distance from this dipole. Okay. So now if we extend this line and draw a perpendicular from here, so this distance and this distance, it will be almost equal. Okay, almost equal, right? So next, what we'll do is we'll find out this distance. So R minus is equal to distance ON or NO plus distance OP, and distance OP is equal to R. Okay, so I can say R minus is nearly equal to, okay, it's nearly equal to distance OP plus distance NO. And if you see this triangle, it is AON. Okay, in this triangle AON, this angle would be theta because this is vertically opposite angle of this angle. So this angle is theta. So what is ON? Distance ON. So I can say in triangle AON, distance ON, distance ON is equal to, or I can say cos of theta. This angle is theta, right? So cos of theta is ON divided by the hypotenuse. Cos theta equals to ON upon hypotenuse, which is AO. Can you see this? This distance adjacent side divided by hypotenuse. Okay, ON divided by AO, right? And therefore ON will be equal to what? AO cos theta. Okay, therefore ON is equal to AO multiplied by cos theta. Take AO on other side, it is AO cos theta, right? So this is equal to, which is equal to, I can say distance OP plus AO cos theta. Okay, and what is OP? So OP is this much distance. It is R. It is distance of point P from center of the dipole. And what is AO? So it is this much distance. Okay, distance between minus Q and O. It is small a, right? So you can say this is equal to R plus AO is small a multiplied by cos theta. Got it? Yes, no? Indran? Okay, good. So then similarly, you can consider the other triangle, this triangle. In this triangle, we can say in the triangle OMB, in triangle OMB, this triangle. Here I can say cos theta is equal to this adjacent side divided by hypotenuse. Okay, so cos theta equals to OM divided by hypotenuse, which is OB, or you can say A, right? Here also I can write this ON divided by A. So ON is A cos theta. So OM, this distance is also A cos theta. Okay, and you can see that this distance R plus is nearly equal to this distance. It is nearly equal to this distance, which is MP. And how do we find MP? So MP is equal to this distance minus this much distance. Okay, it is this distance minus this much distance, right? So we can write this R plus, we can say R plus is nearly equal to, it is nearly equal to what? MP. It is nearly equal to MP, which is this distance OP minus OM. It is equal to OP minus ON. So we know what is OP. So OP is R. And what is ON? So if you take not ON, it is OM, right? Okay. So it is this distance minus this distance. Okay. So OP is R and this distance is what? This distance is A cos theta once again. Okay. So this is R minus A cos theta. This is clear, or is there any problem in this? Then we can substitute this in this equation. What do we get? Therefore, we get potential due to dipole is q divided by 4 pi epsilon naught divided by r plus, this is r plus, it is r minus a cos theta. It is 1 upon r minus a cos theta minus, you have 1 upon r minus, which is r plus a cos theta. Then we have to make denominators same. Okay, denominators of these two same. So we'll multiply this one with r plus a cos theta and this thing with r minus a cos theta. So what will be the denominator? So v is equal to 1 upon or q upon 4 pi epsilon naught, q divided by 4 pi epsilon naught multiplied by, in denominator we'll have this thing multiplied by this thing. So it is a minus b, a plus b, right? So it is r square minus a square cos square theta. Okay, we know what is a minus b, a plus b, it is a square minus b square. Okay, so using that, it's r square minus a square cos square theta. And if you multiply this one with r plus a cos theta and this one with r minus a cos theta, what is left? R plus a cos theta minus, you have r minus a cos theta, r minus a cos theta. So see what will happen. R and minus r gets cancelled. This thing becomes minus minus plus. Okay. So this is equal to q upon 4 pi epsilon naught. Or I will write 1 upon 4 pi epsilon naught. I will take q inside now. Multiplied by, it is a cos theta plus a cos theta, 2a cos theta multiplied by this q. So see, it is q into 2a multiplied by cos of theta. And in denominator you have r square minus a square cos square theta. So once again, see, in all formulae related to an electric dipole, this quantity will be definitely there. It is electric dipole moment. Q times 2a is magnitude of electric dipole moment. Okay, so it is P. So it is V equals to 1 upon 4 pi epsilon naught multiplied by P cos theta divided by r square minus a square cos square theta. Okay, since P equals to Q multiplied by 2a. So this is our formula. Then generally, see, we have made one approximation that length of this dipole is very small compared to this distance. Okay, and that's why we are able to write down this simple formulae for r plus and r minus. Okay, so we'll do same approximation again, that this is very small. A is very small compared to r. Okay, so if A is very small, we have already considered it that A is very small compared to r. We can neglect this. We can neglect a square cos square theta, because if A is very small compared to r, a square will be very small compared to r square, right? Okay, suppose a is 0.1, r is 10. If you take square, a will be 0.01. Okay, compared to what? 10 square, which is 100. Okay, so it's very small. So we can neglect this, and what we get then? So we get V equals to 1 upon 4 pi epsilon naught multiplied by P cos theta divided by r square. Okay, so this is the formula for the electric potential due to a dipole. This is approximate formula, and 99% of time this formula will be used. Okay, we don't even need this formula. This is also an approximation, but we don't even need this formula. 99% of times this formula will be used for potential due to a dipole. So got it? Yes, no? Okay, so P is dipole moment, theta is angle between the dipole, axis of dipole you can say, and line joining the center of dipole to the point P. Okay, so now very quickly we'll see two special cases. So in this case 1 is P, the point P, not this dipole moment. Point P is an equatorial point. So point, I'm sorry, point P is an equatorial point. So it's on the equator. So how much would be theta? 90 degree, right? P is on the axis. If it is on the axis, then dipole length and this line, it will be same line. So then angle will be 0. So these are the two special cases. So P is on equator. So theta will be 90 degrees. Okay. So therefore theta is 90 degrees. And what is cos of 90? Cos 90 is 0. Therefore we can say electric potential due to a dipole on equator is equal to 0. Okay. So this is case 1. And case 2 is P is an axial point. Okay. P is an axial point for a dipole. So theta is equal to 0 degrees. Cos 0 is 1. Therefore, we get V equals to 1 upon 4 pi epsilon naught multiplied by P upon R square. So this is electric potential on axis of dipole and electric potential on the equator of dipole is 0, right? There is another way to understand this. This thing, electric potential at the axis is 0. How come? So you take this dipole, this is suppose, sorry, this is negative charge, this is positive charge, and point P is here. So point P is at the same distance from minus Q and plus Q. So potential at point P due to minus Q and plus Q will be same in magnitude, but potential due to plus Q is positive, potential due to minus Q is negative, and that's why sum of the potentials is 0. It is just scalar sum, scalar addition. Okay. So potential at an equator of the electric dipole is 0. On axis, it is 1 upon 4 pi epsilon naught P upon R square.